So we have already discussed how to calculate potential difference between 2 points in a region of uniform electric field. Now we'll learn how to calculate potential difference between 2 points in case the field is non-uniform. Let's see this with the help of an example of non-uniform field. This is our case where the electric field varies with x coordinate as E is 2 alpha x I cap. I cap means the field is along x axis. This alpha is a positive constant and x is the x coordinate. And in this electric field we are supposed to find potential difference between point A, this one point A, whose coordinate A is 0, and point B, B 0. We have the electric field and the points. Let's see how to proceed for potential difference. We have drawn the diagram. The electric field is given to us, this one. This is simply the strength of field. Direction is known to us. It's along x axis. Point A over here, the coordinates are written over here, B. Now in between A and P, let us take an arbitrary point P whose distance is x from this origin O. This will be the origin. Now from point P, if we move further rightward by a small distance dx, if we move rightward, we'll be moving along the field. So potential would decrease by E dx dV. The change in potential is E dx, but it is decreasing. Voltage is decreasing, so dV will be negative. This is the diagram. We have shown that we are moving from this point in the rightward direction by dx, that is along the field by dx. We observe change in potential V dV. This dV is minus E dx. Minus shows that V is decreasing. Now we have the value of E from here. Let's substitute that value. Minus, this one is E. Now integrate both the sides. Integral dV is this minus 2 alpha is constant. It comes out of the integral sign, x dx. If we put this x is equal to a, small a, we get the potential of point A over here. The limits. If this lower limit of x is small a, here the lower limit of potential comes out to be potential of A. Upper limit, here we will substitute B, small b. Then over here we will get potential of point B. So let's put the limits this way. A, VA, B, VB. Integrated. Integral dV gives us V. Integral x dx gives us x square by 2. This is the thing. Integral dV is V, the limits. Minus 2 alpha the constant, x dx integrated x square by 2. Now we'll substitute the limits. This is the thing. 2 will get a cancel away. And finally this is the result. So here we have used the same concept. But we cannot use it directly from A to B, as VA minus VB is E into AB, because E is changing. So this is the basic way how to calculate potential difference in case the field is non-uniform. Now let us develop a theory of it. General theory. This is our coordinate system, x-axis, y-axis, an arbitrary point P with position vector r. Suppose the field in this region is non-uniform. The field at this point P will have certain direction. Let us assume it to be in this direction. The field at P is in this direction. At P we will have some potential. If we move through some distance, obviously potential will change. Now suppose we are moving through a distance dr, this way, a small distance dr, and this small displacement is in a direction making angle theta with the field. So if we move through a distance dr, the potential decreases by mod E mod dr cos theta. dv decreases, voltage decreases, so dv is negative. E, electric field E, dr cos theta. This we have developed this theory in our previous discussion. Now this could even be written as dot product of E vector and dr vector minus E dot dr. Integrate both the sides. Integrate, the limits are there. We'll put this A, basically here we will put the value of position vector r of point A, and here position vector r of point B. If we bring this minus sign over here, we'll get VA minus VB. This minus sign, we got A to B E dot dr. This is the basic formula for potential difference between 2 points if the electric field is known. This is our general formula. This formula is applicable in all cases, even when the field is uniform. If field is uniform, then this E will come out of the integral sign and we'll get the same thing. Now let us see an example of it, a very important example, that is potential due to a point charge. We'll be using the same method. Suppose a point charge is given to us. The field direction is known. We know that at any point which is at distance r, the field is kq by r square. Anyhow, the problem is to find potential due to this point charge. Let us consider a point P over here. This way. This point P is at distance r from the point charge. We need to compute the potential at point P. First of all, we need to find the field at point P. General expression for field. The direction of field at point P will be this one. It's shown over here. This one will be the direction of field. And the magnitude of this field, let's write down the field over here. This one is the field. Now if we move further rightward by dr, we'll be moving along the direction of field this way. If we move rightward by dr, we are moving along the field. Moving along the field, so the potential would decrease, and we'll have dv as minus E dr. dv as minus E dr. Minus denotes voltage V is decreasing, so dv is negative, and this is the amount by which it is decreasing. We have the value of E. Substitute the value of E in this one. This is minus, this one is the value of E dr. Integrate both the sides. Now here there is a special thing worth noting. We are arbitrarily assuming that when r is infinity, potential is 0. Means at a very large distance, just see this thing, this thing, when this r is infinity, the potential is 0, and when this r has some other value, say r, potential becomes V. This is the basic thing worth noting over here. Now let's integrate it. This constant terms would come out of the integral. Integral dv is V, and this constant terms comes out. We have 1 by r square, that becomes r to the power minus 2 dr. Now here we can apply the direct formula. R to the power minus 2 dr on integration becomes r to the power minus 1 divided by minus 1. This is the thing. This minus and minus will cancel away, and finally we will have this expression. So this is the basic formula. At a distance r, from a point charge Q, the potential is 1 by 4 pi epsilon naught Q by R. So our conclusion is potential at any point at a distance r from a point charge is given by this formula. V is 1 by 4 pi epsilon naught Q by R. The basic formula for potential due to a point charge. Now let us see if we have a system of point charges Q1, Q2, Q3, Q4, and we are supposed to find a potential at point P. Point P is having distance R1 from Q1, R2 from Q2, Q3, R4 from, and so on. Now the potential at P due to this Q1, forget all others, only due to Q1, is this one. V1 is 1 by 4 pi epsilon naught Q1 by R1. Similarly, the potential at P due to this Q2 will be V2 is 1 by 4 pi epsilon naught Q2 by R2. Similarly for Q3, similarly for Q4, and so on, this way. Now, the net potential at point P will be the sum of potential due to all these. Means V at P will be V1 plus V2 plus V3 plus V4 and so on. This would be the result. So in case we have large number of charges, the potential can be found by adding up the contribution of each charge. So this is the whole of calculation of potential due to a point charge.